The NI ELVIS educational design and prototyping platform, based on LabVIEW graphical system design software, is designed for teaching concepts in areas such as circuit design, instrumentation, controls, telecommunications, and embedded microcontroller theory. Today, I'm happy to introduce you to the latest addition to this platform, adopted by leading universities worldwide, the new NI ELVIS II. Hello, my name is Vanessa and I'm an applications engineer here at National Instruments. Over the next few minutes, I'll guide you through some of the unique features that make NI ELVIS a leading educational platform. In this guided tour, we will highlight three important aspects of the NI ELVIS for your laboratory. First, we will see the 12 integrated instruments fully powered by LabVIEW. Second, we will show you how you can leverage the plug-in architecture of partner boards to use NI ELVIS for teaching concepts in multiple classes. And third, we will look at the tight integration between NI ELVIS, Multisim, and LabVIEW that will enable you to bring circuit theory to life. So let's begin by taking a closer look at the NI ELVIS workstation and the 12 integrated instruments. The first thing you'll notice about NI ELVIS is the simple and sturdy design. It is compact, sleek, and suitable for the benchtop of a lab. It has a place to lock it down to prevent theft and holes in the bottom for mounting on other surfaces for easier storage. The NI ELVIS workstation also includes plug-and-play USB connectivity, making it easy to set up in the class or lab. Another feature of the hardware platform is the detachable prototyping board. This has a large breadboard on which you can build your circuits. Here, you can make necessary connections to access signals from the signal rail. For example, connections to power supplies, function generators, analog channels, digital lines, counters, LEDs, D-sub, and more. Here we have clearly labeled B and C connectors to the oscilloscope and the connectors to the isolated DMM. In the NI ELVIS II, the DMM has a precision of 5.5 digits and is isolated. On the other side of the unit, you have the dials that allow you to manually control the output voltage of the variable power supply, from 0 to plus 12 volts and 0 to minus 12 volts. You also have the manual controls of the function generator to control the amplitude and frequency. Notice the LED indicators. These will light up when your hardware is set to manual mode. You can control each of these instruments manually or through software such as the NI ELVIS MX Instruments Launcher, NI LabVIEW, or NI Multisim. Now that I've given you an overview of the hardware, let's show you how easy it is to start using NI ELVIS. As I had mentioned before, the NI ELVIS is a USB plug-and-play device that you can connect directly to your PC through a standard USB 2.0 bus. Because the NI ELVIS II is USB plug-and-play, you can configure, test, and start using it immediately. I have already launched the NI ELVIS MX Instruments Launcher to begin using the built-in instruments. The NI ELVIS MX Instruments Launcher allows you to access all 12 instruments on your NI ELVIS hardware. These instruments include the variable power supply, Bode analyzer, dynamic signal analyzer, arbitrary waveform generator, digital reader, digital writer, impedance analyzer, and 2- and 3-wire current voltage analyzers. For this example, we will be using the NI ELVIS MX function generator. On the prototyping board, I've created a very simple resistor to LED circuit. The function generator is being used to source the input signal of the circuit. The various resistors drop the current supplied to these surface mount LEDs, affecting their intensity. These surface mount LEDs are bicolor. When a positive voltage is applied to them, they light up green, and when a negative voltage is applied, they light up orange. I will start by launching the function generator soft front panel to configure the sources of the circuit. For this demonstration, we'll configure the function generator to output a sine wave at a frequency of 1 Hz and an amplitude of 10 volts peak to peak. As the input voltage is applied, you can see the LEDs alternate between green and orange, consistent with the behavior of bicolor LEDs. You also notice that the intensity of the LEDs are different because of the varying resistor values that we had mentioned earlier. Now, if we increase the frequency of the sine wave, we will expect the LEDs to flash faster. As you can see, the LEDs start flashing faster, verifying the accuracy of our circuit. I previously mentioned you can also switch the function generator to manual mode. You can do this with a single mouse click to click on the button Manual Mode. Now I can use the knob to increase the frequency, and again my LEDs will flash faster. We have now finished our first experiment with NI ELVIS. To summarize, we have seen the USB plug-and-play capability of the NI ELVIS. We have also looked at the 12 integrated instruments of NI ELVIS II, including the oscilloscope, digital multimeter, function generator, and variable power supply. We use these instruments to verify a resistor circuit that is used to limit the current supplied to LEDs.